to all of you. In this class we will discuss about the phasor estimation techniques. One of the phasor estimation techniques is DFT, that is the Discrete Fourier Transform, and already we have discussed that in case of PMU the main phasor estimation technique that is used is the DFT. So, that is why in this particular class we will discuss about it, what is that and how to write it and what are the mathematical formulation, and we will also do one assignment if we will take some sample data. So, how to calculate the phase angle or the magnitude of the voltage current using the DFT. Now, as far as the phasor is concerned, how to define a phasor? If we will say this V a phasor, so it has a magnitude and also it has angle. So, these two together, the magnitude part is the magnitude part and this is our angle part. So, magnitude and angle together form the phasor. Now, one more point we have to also keep in mind when we call about this phasor, we will talk about the phasor, the frequency is also important. This fundamental frequency, if it is 50 hertz. So, at what frequency this particular phasor is calculated, that is also important. As far as the magnitude and phase angle both are concerned, if you will vary this frequency, then their corresponding values are going to be changed. So, that is why at particular frequency the magnitude and phase angle together called as the phasor. If you see this particular picture, here we have taken one Vm, one phasor position at t is equal to 0, and you can see this is the rotational plane and this is our sinusoidal plane, that along x axis we have taken this time axis, this is t, and here is our magnitude Vm, and this is how this t0 starts from. T0 means it is the starting point of the phasor. Now, when this phasor rotates at certain frequency, as we have discussed, this is angular speed, that is omega is equal to 2 pi f. 2 pi stands for 360 degree and this is our frequency, that is 50 hertz. So, this angular frequency, this radian per second, so it rotates, and from t equal to 0, let us say it starts from t equal to 0 here. So, this is the position of t equal to 0, this is the position of the phasor, and when this phasor rotates and it reaches to t equal to t0 and the corresponding phasor position is here, it is t equal to 0. That means, this is the starting point, so let us say this is the another point. So, if further it moves away, let us say t is equal to t1 is equal to t0 dash, so obviously, so it will come to another point in the t axis, along the t axis. So, this particular phasor position which is shown here and here together altogether equal. Now, to represent the position, we took also sometimes this real axis, this is our real axis and this is our imaginary axis. If I want to this decompose this particular phasor, it is a complex number basically, it is a complex number and which has like provides the RMS value of the signal, and angle provides the instantaneous position of the signal. At what angle this signal is rotating at particular time stamp, we can always access it. That is what this real axis will tell the real part of this particular phasor, and this imaginary axis will just say what is the imaginary part of the signal. That is basically the complex form of representation of the phasor quantities, phasors. Now, if I will just write here this V a phi a, so how to write in complex form? This will be V a cos phi a plus j V a magnitude, basically this is magnitude, V a magnitude and then sine of phi a. So, this is our the real part and this is our imaginary part. So, along this real axis we can take how much this real component, and along this imaginary axis we can take the real imaginary component, taking the resultant. So, finally, we will get this V a magnitude. That is what is the complex form of the phasor, and also sometimes we represent in terms of like exponential form, also in polar form. So, there are three forms basically we follow to represent the discrete Fourier, the phasors. The first one is, this is our polar form, this is our rectangular form, and this particular signal also can be written, this V A phasor also is equal to V A, this magnitude e to the power j phi. This is our exponential form. Now, this DFT, discrete Fourier transform, is one of the signal processing techniques which is used to estimate the phasors of the voltage and current signal. Let us say we have 3 phase voltages, 3 phase currents. So, if we have this one phase voltage and again another phase voltage with 120 degree apart, also we have current phase, let us say this is V A and this is I A, and this is all instantaneous with respect to time we took it. So, this is small V A t and this is small I A t. Similarly, we have other phase voltages and other phase currents. So, what is DFT? This stands for, the abbreviation is DFT. The DFT helps in providing the magnitude and phase angle of corresponding voltage and angle. If you will see how it will be, if it is 5 volt, the signal is of plus minus 5 volt voltage signal. Now, we will expect that DFT will provide a magnitude curve like this with respect to time. Now, similarly, what will be the angle information? The angle will just rotate within 180 degree repeat. So, this is 180 degree 360, 180 degree 360. So, within a cycle, this is one complete cycle of the angle like this. So, this magnitude, this is the magnitude of the signal and this is the angle of the signal. So, this magnitude angle we are interested to extract using this DFT of this particular signal, sinusoidal signal, voltage and current, which are basically the power system. I am just talking about in terms of PMU or relaying practice or relaying field. You will see in the subsequent slides for protection approach, in case of digital relays, the phasors of the voltage and current are very important, because when the relays are basically sequence component based relays, in some cases we use the positive sequence component of the voltage or current, or we can use the negative sequence or zero sequence components of the voltage and current. So, in that case, to calculate the sequence components, so we need the phasors of the voltage and current. So, that is why in case of relays also we need some phasor estimation techniques, and just way we need in PMUs. Let us start with this mathematical expression of this DFT. This Vk is equal to 2 by n, summation of n is equal to 0 to n minus 1 Vn e to the power minus j 2 pi k small n by capital N. Let us define what are these symbols. What is this k? The k is the order of the harmonic, order of the harmonic signal present with the fundamental one, with the fundamental signal. So, as already we have discussed in power network, we have fundamental signal, also we have harmonic signals. So, these harmonics are coming due to the presence of electronic devices or nonlinear loads also we have. So, due to that we have harmonic signals which are present along with our fundamental signal. But remember, for our further processing using this phasor measurement unit or digital relays, we need the fundamental component of the voltage or current signal, not the harmonic. Yes, of course, in some cases intentionally we compute the harmonic components of the voltage current signal for our purpose. In some cases, some like if you just recall in your BTech level, we studied the second harmonic restrained differential relays, or some and second harmonic component is also used for protecting the transformer. In some cases also we need nowadays in advanced protection strategies, we need some harmonic signals to analyze some protection issues. So, intentionally we also calculate this frequency harmonic components for our application control or protection purpose. So, here this K stands for the order of the harmonic present in the fundamental signal, and this N, capital N, stands for number of samples per cycle. So, we have discussed in our WOMS technology class that we sample the signals at particular sampling frequency. The sampling frequency we stands for Fs is equal to our sampling frequency. So, if our fundamental frequency is 50 hertz. So, our fundamental time period will be 20 millisecond. It is basically 1 upon 50. So, these are the symbols we have to consider, and also here sometimes we write Ts, the sampling time period, that is 1 upon Fs. So, these are the symbols we use for our discrete Fourier transform analysis. Now, this capital N is the number of samples per cycle, and this V n, sometimes also in some cases it is written small v n. This small v n is our sample values of the signal. Suppose one signal we have sampled at particular sampling frequency, if this is my analog signal and the corresponding samples I just reconstructed here. So, this sample values we call it, this is our time axis and this is my small v t, and this signal is basically the analog signal. And if I will just sample down this analog signal, so we will get the digitalized or discretized signals. So, this is known as discretized signal, that is in discrete time domain. I can write here k t. This is at certain time interval we are basically sampling it. So, we call it KTS. This small t is represented by KTS, and along this y axis we have v small n. Now, this n stands for the number of samples we have taken for a particular period. If I took 2 seconds, so for 1 second 1000 samples, if I will take sampling frequency as 1 kilohertz. So, if it will be 2 seconds if I will consider, so there are 200 samples per 2 seconds. So, if my sampling frequency is 1 kilohertz. So, in that sense 20 samples per cycle is our number of samples, that is n, and this t stands for KTS, because let us say this n is equal to 1 or k is equal to 1 here. Sometimes also we took it NTS also, the position of the sample. This n stands for position of the sample. When n is equal to 2, so here is our n is equal to 1 or k is equal to 1, this is 2 Ts, and this position is 3 Ts, and this position is 4 Ts, 5 Ts, so on. That means the point here is that the number of samples positions should be indicated in discrete domain, not in continuous time domain. This is a continuous time domain signal and this is a discretized time domain signal. That is why the name is discrete Fourier transform. And in discrete Fourier transform, the name transform means we are transferring this particular discretized signal to a frequency domain. This is time domain, this one is discretized signal in time domain, discrete time domain, and we are converting to a frequency domain signal, because we are going to calculate the phasors. The phasors means the frequency domain is must. We should know at what frequency we are going to calculate the RMS value of the signal and phase angle of the signal. So, that is why this is how this is our discretized time domain signal, and we are converting to this frequency domain signal for calculating the magnitude and phase angle. Now, if you see that another term here, it is as I said that small n, that is our number of the position of the sample in a particular string, and this n small n lies between 0 to n minus 1 for this case, because we are discussing a full cycle discrete Fourier transform. There are different types of DFT, the full cycle DFT, half cycle DFT, cosine DFT, sine DFT. So, in that case we are first discussing the full cycle discrete Fourier transform. Now, if we decompose this above factor, this equation, we have real part and also we have imaginary part. This 2 by n summation of n equal to 0 to n minus 1 V n, this is small v n into this sine 2 pi small n by capital N. This is one expression, and this is our imaginary part expression, this is our real part expression. Now, in this case this k is considered as 1. Why? When this k is equal to 1, it stands for the fundamental frequency component. When k is equal to 2, so it will just provide us the phasor value of the second harmonic component of the signal. If k is equal to 3, so it will provide the third harmonic component of the signal, the phasor value of the third harmonic component of the signal. That means so on. So, this we can vary this k according to our requirement, but for this case we are considering the fundamental component of the signal. After knowing this imaginary part and real part, so real and imaginary square if we take, so we will get the magnitude and the tan inverse of this imaginary to real part. So, we will get the phase angle of the corresponding voltage, or let us say current if you want. So, we have to also decompose the current in that manner. We will have the real part, imaginary part, and then squaring together we will get the magnitude and also phase angle. This is one table, you can take it as an assignment that how to calculate this particular signal, that this xi, sometimes we can also write it xi, or this is small x n, or this discretized signal n, basically n stands here the sample position 1, 2, this is equal to 3, n is equal to 4, and so on. We have number of sample positions. This is the first sample, this is second sample, this is third sample, fourth sample, and so on. Now, if you could remember in previous part, the real part is cos 2 pi n by capital N, keeping this k is equal to 1. If you put this, so this will be our, these are the corresponding magnitudes, and similarly this is our imaginary part, sine of 2 pi n divided by n. So, when you calculate this I or n, we can replace it whatever you like, this n equal to 1. So, this is the corresponding value. When this I is equal to or n is equal to 1, this is the corresponding value, and here you should put n is equal to 20, because the sampling frequency we have mentioned here 1 kilohertz, this is 1 kilohertz. So, these are after getting this cosine factor, sine factor, then we will multiply the corresponding x n value with the sine and cosine factor, and finally we will take, if I will just denote this total factor as a and this total factor as b. So, this summation of a, let us say, is equal to a 1, summation of b is equal to b 1, or in either way we will write. Now, this magnitude is equal to a 1 square plus b 1 square root over, and angle part of this signal is equal to tan inverse of b 1 upon a 1. So, this is one kind of assignment, you can take it and you can calculate the corresponding magnitude and angle. Here we will go for half cycle DFT. In case of half cycle DFT, we basically go for half of the sample values. Let us say in a sample string we have 20 samples, n stands for 1, n stands for 2 up to n is equal to 20. So, if we will take total 20 number of samples, that is n capital N is equal to 20, and if we consider the whole samples, 20 number of samples, and we calculate the DFT, then the DFT known as full cycle DFT. If I will take only 10 samples up to 10 when n is equal to 10, then in that case the DFT is known as half cycle DFT. That is what is mentioned here. In that case only the difference will be in case of number of samples. If you just go back to the previous expression of the full cycle DFT, here we wrote n minus 1. In this case the number of samples starts from n is equal to 0 to n minus 1, but here in this case the number of samples starts from n equal to 0 to n by 2 minus 1. So, we are taking here half of the samples. If 20 is the figure for number of samples per cycle, so here in this case we will take 10 samples per cycle, half cycle, not per cycle, the half cycle, 10 samples per half cycle. So, half cycle data or samples we will take. Now, as other things remain constant, that is V n cos 2 pi small n by capital N, and this is our real part and this is our imaginary part. Here is V n sin 2 pi small n by capital N. This is our imaginary part, and here there is no change in n. Does not mean that here we will take n by 2 in place of n. No, here this n stands for number of samples per cycle. So, it is not necessary, it is not required to take this n here. If we will take this magnitude and phase formula, it is same as previously we did for the DFT. You can see here in case of DFT, here we have taken the same. Now, coming to this another part, that is a cosine transform of the DFT, that is cosine part of the signal, that is 2 by n, n stands from 0 to n by 2 minus 1, and here we have V n small v n and cos 2 pi small n by capital N. Now, this is the real part of this particular signal. What about the imaginary part? If I do not know the imaginary part, then how to calculate it? It is in this way. If this is my real part and this will be my imaginary part, what I will do here, if I will put n minus capital N by 4, so I will get the imaginary part of the signal, that is the sine part of the signal, because the difference between this, if I know cos theta, then how to know the sine theta? Then just making minus of n by 4 points, 1/4 signal or minus 90 degree, sine of 90 minus theta is equal to cos theta. So, in that case let us say I have one string of data, n is equal to 1, n is equal to 2, n is equal to 3. Let us some values we have 8.2 or 8.6, 8.3, 8, n is equal to 4, n is equal to 5, some values, arbitrary values. I am just writing n is equal to 6, let us say this is 9 or 9.1. So, these are the sample values and so on, it goes up to n is equal to 20, because we are discussing about this 20 samples per cycle data. Now, the question is, if this is my cosine part, so how to make it the sine part? From the same data I will construct my signal. So, this is like this. If I am here, let us say n is equal to 4. So, how to make the particular sample for this Vc n minus n by 4? So, from where I should start? If this is, that means n is equal to, now it is 4, that n minus n by 4 means n small n minus 20 divided by 4, that is 4. If I will come like number of samples I have 20 by 4. So, fourth before the fifth point, before 4 points I have to move. N by 4 means fifth point, here it is. If I have the signal, here is my n by 4 and here is my n by 2 and here is my n stands. So, number of samples here is n by 4 and here n by 2 and here is n. This is 20 number of samples, here it is 10 and here it is 5, here starts from the 1. Now, that means I have to start from here, n is equal to 6, because I have to go back 5 samples. So, here is my n minus n by 4, that is 6 minus 5, that is equal to 1. So, this sample should be taken into consideration. If I am starting from here, n is equal to 6 and this is for my real part sample value, and so for imaginary part my sample position will be 1 and this 8.2 is the corresponding sample value. If I will just want to write here for n is equal to 6, so it should be 8.2 plus j 9.1 and so on. So, if I will take n is equal to 7, so my, let us say this is for n C n and this part will be n dash is equal to, so the 7 minus this 5, it will be 2. So, that means it will just keep on sliding. This is 7th position. So, here it will be my real imaginary part. If it will be 8, so the real imaginary part will be 3, and if it is 9, then it will be 4, and so on. So, that means if I know a string of data, it is not necessary to calculate the sine part. From the cosine part, from the same symbol, we can always calculate the real part as well as the imaginary part to find the magnitude and phase angle of the signal. Now, we will go for the discrete Fourier transform part. This is the DFT we have discussed. In case of DFT, we have full cycle DFT, we have half cycle DFT, we have cosine DFT. Now, we will discuss about the discrete Fourier transform in recursive manner. What is a recursive DFT and why we are interested for this recursive DFT? In case of recursive DFT, one advantage is, well, we will just calculate in a windowing manner. What is the window word first we will discuss, then we will go for recursive DFT. If this is one sinusoidal signal where I have taken 2 cycles and I just want to calculate the corresponding magnitude phase angle recursively, not iteratively, it is recursively it will move. This is my first window which is having 20 samples per cycle. It starts, the n starts from 1 and it ends with 20. Now, next window will move to the another label, this is n is equal to 2 and n is equal to ending one is 21, so on. That means, this window is moving inside the signal and taking 1 cycles and 20 samples per cycle, and it moves ahead, and this kind of movement is known as windowing approach or window approach of the in calculating the phases of the signal. Now, if it is so, then if for this particular first window we have quite particular magnitude of the signal and corresponding angle also will be here. Similarly, for the second window we will have some magnitude point here and the angle point here and so on. So, if you just see, then corresponding angle, the magnitude will be like this and the corresponding angle goes on like this. So, we will see this particular picture in more clarity the next PPT or slide. Now, this is our first window, this is second window. So, now we will come to the recursive DFT part, that with using this recursive DFT we can minimize the time of computation. In DFT, if we just every time we are going to this, let us say this is window 1, for this we will calculate the DFT and the corresponding magnitude and phase angle we will calculate. Similarly, the second window also will apply DFT and we will calculate the corresponding magnitude and angle. So, it is time consuming affair. Every time we are computing the imaginary part, the real part, and again the magnitude and phase angle. So, we are again, if you could remember our table, so this kind of computation is happening every time. So, this cos theta sin theta part, then this x I into cos theta x I into sin theta, this computations are compulsory. So, every time for every window we are doing this, the computer is doing the same exercise time to time. Now, but what will happen to remove this, to avoid this kind of computation for every window? So, we will just do one technique that is known as recursive DFT. In this case, only once the DFT will be calculated for the first window. What we will do here? We will just calculate the DFT for the first window, and subsequent windows will not, we are not going to calculate the DFT anymore. The first DFT will be utilized to calculate the magnitude and phase angle of the second window or 20 samples per cycle data. And similarly, for the next window, we will take the help of previous window magnitude and phase angle, and then we will proceed, and so on. So, this kind of approach is known as recursive DFT. In this manner, we can save the computational time, which is basically happening in case of discrete Fourier transformer, and where we are calculating the DFT for every window for finding the magnitude and phase angle of the signal. Now, this is how this samples of 20 samples per cycle, here 20 samples, here it starts from 1 and it ends with 20, and this is the magnitude part and this is the angle part. You can see here how these angles are varying. This is here one cycle 20 here at this point, and here another cycle, the angle varies like this. If you will just calculate the angle between two samples at this point, it will be 18 degree, because we have 20 samples, angle is basically 360 degree, 360 degree by 20. So, it is going to be 18 degree. So, between two samples the angle difference is 18 degree, that is like this. So, for every, if you will take a window kind of approach, this is my first window up to 20th, first window, and this will be our second window, where it will start from n is equal to, this is n is equal to 1 to n is equal to 20, and next window will start n is equal to 2 to n is equal to 21, and similarly, and the third window will be like this, and so on. This window will keep on progressing, going ahead, proceeding ahead to find the corresponding magnitude and phase angle. For this first window, for the first window, this is the magnitude and this is the corresponding angle, and for the second window, this is the corresponding magnitude and this is the corresponding angle, and for third window, this is the third window, this is the magnitude and this is the corresponding angle, and so on. So, when this window ends within a cycle, so this is the end of this particular angle, or this is the end of corresponding magnitude. Now, we will come to this mathematical expression of this recursive DFT or recursive discrete Fourier transform, that here this V, the capital V r plus 1 is equal to capital V r into this e to the power j 2 pi by n plus 2 by n small v. So, this is small v, small r plus capital N minus small v r into e to the power j 2 pi by n. Now, I want to explain this particular expression clearly, so that we will understand. So, what is the basic difference between this recursive DFT and the only DFT. Now, if you could see what is this capital V r plus 1. If I have a signal, as already we have discussed in the previous slide, that this particular signal is moving ahead, and this is my first window and this is my second window. So, this arbitrarily, let us say I can start from any window my for calculating my phasors. Let us say this is my rth window, that is what the meaning of this r, small r. If I will take, this is the say last next window, so this will be r plus 1th window. Now, this for this particular window r plus 1, so that will be, this will be my phasor VR plus 1. Now, how to express this? This VR is the previous window DFT value. So, what is this VR? The VR is the DFT, 1 cycle DFT, 1 cycle DFT of earth window data sample. This data may be we have voltage data or we may have current data. Now, this earth window data sample DFT is VR, this is capital VR into this J 2 pi by n. Why this J 2 pi by n? Between the two windows, the difference between this angle difference is how much? 2 pi by n, that is 18 degree. If we will take n is 20 samples per cycle. And what about the second term? We have two terms. The first term is basically the DFT of the first window, and the second term is what? The difference between the new sample and the outgoing sample. This is the magnitude part of this particular sample and this is the angle part. We have to multiply the angle also. Now, this what is this new sample in this case? If you consider this is the window, just I will make it in a different shape. You can understand easily that this dashed line is my earth window and the solid one, this solid one is the corresponding new window. We are moving from old window to new window. So, of course, when you will move from one window to first one window to other window. So, within consecutive window we have one old sample is going to be rejected and new sample is going to be entered. So, in this case if you will see that this is how this window ends here and this is this was my last sample and this is a new sample which is entered inside. If you will tell like this 20, first n is equal to 1 to 20 and next n is equal to 2 to 21. Now, this one sample, the first sample is discarded and the 21st sample is entered to the fresh window. That is what the meaning of new sample and outgoing sample, and the name is like this. The new sample I can write VR plus n and this is my outgoing sample. Okay. So, if this R is equal to 1, then if n is equal to 20. So, this 1 plus 20, that is basically 21 is my new sample and 1 is the old sample. So, old sample is discarded and the new sample is entered to the window. The difference between these two magnitude, sample values in magnitude. So, this difference between these two basically is the difference, I mean the what gap exists between the two samples, new sample and the old sample, and multiplying this angle we will get the phasor information. Now, the question comes between these two samples the information, the gap will be 0 throughout unless until any disturbance is going to be inserted. In fact, the first sample is basically similar to the 20th sample of the next window. The first sample is just similar to my 21st sample of the next window. The difference is basically 0, but when any fault occurs, or any disturbance occurs, now the signal magnitude increases to another level. Now, the difference, if you see this window moves on, but however, when the window moves or it reaches within this changed signal part, then it will see some difference between these two samples. The new sample and the old sample difference will be significant when this window will reach within the disturbance area. This is our disturbed area, or I can show here this is my signal before the disturbance and this is a signal after the disturbance. Let us, this current magnitude has been increased to another level after the disturbance. Now, this window will keep on moving, and when this window moves inside the disturbance area, now there is a basically significant change between these two samples. Now, this is another part which is known as frequency error analysis in DFT, and before going to that let us just give some remark on this recursive DFT, that in case of recursive DFT we observed that only we have to calculate the DFT once. This is our for this VR, and the rest of the window, for the rest of the window we are not going to calculate the DFT time to time. Just taking this second expression, we can just add to the DFT value of the previous window, so that we can calculate the DFT of next window. So, in this manner the recursive DFT saves the time, and also in computational wise it is quick and we can save the time. That is our aim of this recursive DFT. Coming to the error analysis, that is a frequency error analysis, as we are operating in the frequency domain, as far as the DFT or recursive DFT are concerned, the operation is frequency domain. Now, if the frequency of the system varies than the nominal values, let us say we have 50 hertz, if the frequency varies something like 49.5 or 49.8 hertz, or sometimes it increases to 50.1 or 50.2. So, in that case, how this magnitude and phase angle which are calculated using the DFT or recursive DFT, they are going to be affected. That is what the frequency error analysis. To have this, we have certain steps mathematically and we have to understand it. Here is the first signal, we have taken step 1. This is step 1, we have taken one instantaneous signal, that is xt in time domain, where the signal is expressed like this, that is x, capital X is the magnitude of the signal, cos omega t plus phi, it is a cosine function, this phi is the phase angle of the signal with respect to certain reference. And this small x k is the signal in discrete domain, that is small x still exists, this is in analog or infinite, that is a continuous time domain, and this small x k is the signal in discretized time domain. And only the difference here is, in place of t, this small t we have to replace k t s. That is a difference, as already we have discussed that for a signal, if it is in time domain t and in discrete domain, when you will just convert, this small t will be replaced by k t s. The signals samples are basically sampled at within a certain interval. So, this distance is basically k t s. This t s is the sampling time interval. Within two samples, consecutive samples, the time gap is basically known as t s. Now, let this particular signal, again we will write x e to the power j, we will just denote x, small x bar is treated as capital X into e to the power j phi. Now, by rewriting this x t in exponential form, like we will just decompose, like cos theta is equal to cos e to the power j theta plus cos e to the power minus j theta divided by 2. So, in that form we will write x as this is the theta omega t plus phi. So, first one will be e to the power j omega t plus phi plus e to the power minus j omega t plus phi. As we have already taken, just by decomposing this e to the power j omega t into e to the power j phi plus e to the power minus j omega t into e to the power minus j phi. Now, in place of this, if we multiply x with all together x, so this expression can be written as we have abbreviated here x small x bar, the small x bar into rest of the term e to the power j omega t. Now, let us say f naught is our nominal frequency, and due to some disturbance we have a frequency deviation than our nominal frequency, that is, let us say that is delta f. This delta f is the frequency deviation, and in that case how to write it? What is the frequency change in frequency? That will be f naught plus delta f. Earlier it was f naught, now this f naught dash is equal to f naught plus minus del f. This frequency deviation when we added, or it may be subtracted. Now, if by considering this omega as with the changed frequency scenario, this x here can be rewritten. This is how our expression was for the previous expression, like we have a DFT. If you could remember the DFT of a particular signal, 2 by n, k is equal to 0 to n minus 1, x of k plus r e to the power minus 2 pi k by n. Now, what this r stands for and k stands for? Already we have discussed capital N is the number of samples per cycle, but here this r stands for for what window we are looking for, rth window, r plus 1 or r plus 2 and so on. Now, what about this k? K is basically the number of sample position, as if we have taken the previous case n, small n. So, that this k stands for the sample position and this r small r stands for the window position or window number. Now, by keeping this in mind, so this xr can be written in this manner, where this this capital N can be written as T divided by Ts. This is our formula, because T is basically 20 milliseconds and Ts is equal to 1 milliseconds. So, how to get this number of samples? The relationship between this capital T and Ts is equal to 20 divided by 1, that is 20. That is how this N, T and Ts are related to each other. Now, in place of capital T also we can put as 1 upon f naught. Putting all this, we will just get 2 upon n, this x k plus r e to the power minus j 2 pi k by n, and this is how our recursive DFT part. I should not discuss about this part, because already we have discussed how to take the recursive DFT. This is the first window, rth window, and this is by r plus 1th window. If this is the DFT for my rth window, so this will be my DFT using the recursive concept for x plus r plus 1th window. Now, this is one other symbol we will use here, omega is equal to w, or you can say, because omega is our radian frequency, small w, e to the power j 2 pi by n. Now, by putting all this expression, so this will be my final expression for kth window signal. Now, you can see here that very clearly that in this expression, that this f naught plus delta f is represented here very clearly as far as the frequency deviation is concerned. And that is why, if previously, if you could see here, our expression was here, that the frequency for this case was f naught only, but now in this case the expression is f naught plus delta f. So, as if this is the case, so obviously the magnitude of this particular x of plus r1, this magnitude and also the phase angle are going to be affected, because the frequency has been deviated from the nominal values. This is how this is for recursively, if you are running this, I stands for one recursive window. If you just code this mathematical equations, so slowly you will find the window will move ahead using this I. This is basically a for loop case type. So, this is my signal. If it is so on moving, now this window will keep on moving one by one. This is how it will just move ahead. So, if we will just move ahead, then we will find the corresponding magnitude and the corresponding angle also. Already we have discussed this. Now, the question here is, due to this frequency deviation, you can see here, due to this frequency deviation, let us say we got some magnitude with f naught is equal to 50 hertz. Now, we will get some deviation in the magnitude part if f naught dash is equal to either 50.1 or with some this f naught dash is equal to 49.5 or 49.8, whatever the frequency deviation. That means the difference between these two magnitudes are basically errors. If my frequency is deviating from 50 hertz to another frequency value, that deviation is basically the error in terms of, like, maybe it is in magnitude part or also in the angle part. So, this is how today our class we did. We have discussed the one of the important Phasor estimation techniques, that is the DFT, Discrete Fourier Transform, and again also we have discussed recursive DFT, that is recursive Discrete Fourier Transform, and also we have analyzed the frequency error part which is going to be happen in our magnitude and phase angle case. Thank you all.